Now we start the second part of Intermolecular Forces, Unit 2, which deals with hydrogen bonding and other types of bonds that are there. And so I'm going to start sharing my screen with you, and then we'll go through the objectives. And then please remember that at the end of the slideshow, there are sets of questions for a self-check. That in that way you will know that you have understood the concepts clearly and be able to answer any question. A reminder, please do the homework assignment and make sure that slowly and steadily you keep at it so that it completes on time without asking for any extension. Here, the second unit in chapter 11, Intermolecular Forces, is the hydrogen bonding. Basically, we want to know the origin, properties, and the effect on physical properties and its importance on marine life and biological systems. So the question comes, again, this part is a repetition from the ending towards the first unit as a recap. How does hydrogen bond form? It forms when small atoms with high electronegativity or have lone pair electrons present. Such types of atoms are nitrogen, oxygen, and fluorine. And one of the atoms in the bond, of course, as the name suggests, is hydrogen. The strength of the bond ranges between 4 to 25 kilojoules per mole. When we compare the properties for the effect of hydrogen bonding on group 4 and group 6 hydrides, we see that the molar mass of the compounds in group 6 increases steadily from sulfur to tellurium and is higher than the boiling point for the group 4 elements down the group. As the molar mass of the compounds in group 4 increases, the boiling point increases steadily, gently with a comparable slope. The boiling point values are higher for groups 6 elements as compared to those of group 4 elements. However, the hydrides of group 4, methane, and hydride of oxygen, group 6, indicate a large variation in their boiling point. This large difference can only be explained on the basis of the dipole-dipole interaction and the hydrogen bonding between the water molecules. Methane, by its very structure, is a nonpolar symmetric molecule. The boiling points of hydrogen continued with those comparison between 4, 5, 6, and 7 elements. We see that boiling points increases. Polar molecules show higher boiling point. However, the polarity of the dipole of water is much larger than that of ammonia and HF, and so its boiling point is much higher. Next, when we compare the hydrogen bonded compounds based on their molecular mass, we see that boiling points of simple hydrogen containing compounds, almost which are similar to that of water, which has a boiling point of 18 grams per mole. Then hydrogen fluoride is 20 grams per mole. Ammonia is 17 grams per mole, and methane is 60 grams per mole. And we see that the unusually high boiling point for water at 18 grams per mole is a result of hydrogen bonding. Hydrogen bonding and the unusual properties of water. Ice flows because it is less dense than water. The hydrogen bonds allow the molecules in the liquid phase to approach closer than normal for non-hydrogen bonding liquids. This is why water has a maximum density at 4 degrees Celsius. Ice has an open lattice-like structure. Ice density is less than that of the liquid, so solid floats on water. One of the very few substances where the solid is less than the liquid. Mostly we find that the solids are much denser than the liquids, and therefore they sink to the bottom. Hydrogen bonding in DNA helps to form the double helix structure. As you can see, the bonding is between nitrogen, hydrogen, oxygen, hydrogen, and it is repeated in the various amines or bases that are there. And you can see in the picture how the base is expanded to show the repeated molecules and bonds that are there. And this is a molecular modeling showing hydrogen bond in 2D for the DNA molecule. Next, once we do the hydrogen bonding, we come to the other forces that we have, other van der Waals intermolecular forces, and they are the induced dipole forces, which we also call them as Debye forces. Polar molecules like water can induce or create dipoles in molecules that do not have a permanent dipole. Why is this important? Various gases such as oxygen, nitrogen, hydrogen, and carbon dioxide are not very soluble in water because they are essentially nonpolar. But oxygen must be dissolved in water to sustain fish life. This is due to these dipole-induced forces that the polarization can occur. And how the polarization occurs is shown in this particular slide. The dipole of water induces a dipole in oxygen molecule by distorting the electron cloud, which is uniformly distributed before it comes into contact with the dipole. And you can see how it, which is circular on the left-hand side, tries to take the oval shape. And same thing, when we have polar ethanol, we can introduce a dipole in a non-polar subject, a material substance like iodine, which is shown at the bottom of the slide. Forces involving induced dipoles. What happens? How can non-polar molecules such as oxygen and iodine dissolve in water? The water molecule induces a dipole in the oxygen electron cloud, and this causes a temporary dipole-induced dipole effect, which allows it to become soluble. Solubility and molar mass induced dipole forces. Hydrogen, nitrogen, we compare three gases, and this is from the Lang's Handbook of Chemistry, which is still used for many measurements. The molar mass of hydrogen is 2.01, for nitrogen is 28, and for oxygen 32. And we said that the solubility of hydrogen is about 1.60 times 10 raised to minus 4 grams of the gas and 100 grams of water. For nitrogen is 1.9 times 10 raised to minus 3 grams of the gas in 100 grams of water. And for oxygen, it is 4.34 times 10 raised minus 3 grams per 100 grams of water. Now, these measurements are very important because they are required for the sustenance of life in water. The degree to which an electron cloud of an atom or in a molecule can be distorted is measured by the polarizability. The larger the molecule, the more easily it is polarized. As the electrons in the molecule become more loosely held and more spread out, the greater the degree of polarizability in the molecule. This explains the trend we see in solubility. Now, forces involving induced dipoles. This is a second set of dipole-dipole interaction, which is considered as the induced dipole. Formation of a dipole in two non-molar I2 molecules is shown. So two non-polar atoms or molecules depicted as having an electron cloud that has a time-averaged spherical shape. Now, because of the induced dipole, momentary attractions and repulsions between nuclei and electrons in neighboring molecules lead to induced dipoles. Correlation of the electron motions between the two atoms or molecules which are now polar leads to a lower energy and stabilizes the system. London Dispersion Forces, sometimes called as induced dipole, is present in all atoms, molecules, ions due to the unsymmetric distribution of electron cloud, higher molar mass, which has more electrons. Continuation, London dispersion forces exist between all molecules. The dispersion forces are a function of molecular polarizability. The polarizability of a molecule is measured by the ease with which an electron cloud can be distorted. Larger the molecule, the greater the number of electrons, greater the polarizability, greater the surface area available for contact, and greater the dispersion forces. London dispersion forces therefore increase as molecular weight increases. Polarizability and its effect on boiling point and shape. Ease with which the charge distribution in a molecule can be distorted is a measure of squishiness of the molecule. What does boiling point tell us? Intermolecular forces increases with increased polarization of bonds. Strengths of forces impact boiling point. Boiling point increases with molecular weight and with surface area. What is the effect of shape on polarizability and due to? Branching tends to lower the surface area of the molecule, where these London forces are the most pronounced. Now we see a table of boiling point for halogens as well as for the inert gases, and you can see that the boiling point in Kelvin increases from fluorine to iodine, and same thing from helium, which is 4.6 K, to xenon, which is 166.1 K. The helium is much larger in size and has a more higher atomic mass as compared to helium. Now, once we've done all the summary, then studied how the forces are brought about, we have just a brief recollection of summary for the intermolecular forces so that it becomes very helpful and useful in deciphering and determining what type of bond is present between different types of molecules based on their mass, their boiling point, etc., which are basically physical properties, including the solubility. Hydrogen bonding is between X and H and Y, where X and Y have lone pair of electrons, and as well as they can have different electronegativities and consist of the bond is formed between F and O. That is fluorine, nitrogen, oxygen. Dipole forces. Dipole moment depends on electronegativities and molecular structure. And so if a molecule has an electronegative atom in it, it is possible in its arrangement that it can attract and cause a dipole, induce a dipole moment then. Induced dipole moment of polar molecule and polarizability of the non-polar molecule, for example, water and iodine. And London dispersion forces are considered as the forces that are responsible for the boiling points and melting points of gases such as inert gases, because the polarizability depends on the molar mass, and it is induced, and it is a temporary attraction. The electron cloud is distorted for a very short period of time, during which a dipole is set up, and the molecules or atoms come together. So the pathway to how does then one identify what type of interacting particles are there? And this leads to a pathway summary to identify intermolecular forces, interacting particles. And the first questions are ions involved? If the answer is no, then are polar molecules involved? If the answer is no, then we say that the forces most probably which will come into play are the London forces, which are the induced dipole moments. On the other hand, if the question asks, are ions involved? And if the answer is yes, then there are two stages over here. And with the question, are polar molecules involved? If it is yes, then you have ion dipole forces. And if it is no, then we have ionic bonding. Coming to the center, the next question is, are hydrogen atoms bonded? No, that means dipole forces. Yes means hydrogen bonding, especially to oxygen, nitrogen, and fluorine. Now comparing the intermolecular forces, just look at it and you can see, identify which has the higher boiling point, identify and explain your answer. Explain your answer. We see that the question is nitrogen. The two gases are nitrogen and oxygen. We see nitrogen has a boiling point of 77 K, oxygen is 90 K. And both the molecules are nonpolar molecules, and only London dispersion forces come into play. Nitrogen has a lower molecular weight, while oxygen has a higher molecular weight. Beyond that, you can even compare the molecule, a compound like HCl, a covalent compound, or an ionic compound like HCl, with that of argon, an inert gas. And we say that both HCl and the molecular mass of both HCl and argon are very close to each other, but the boiling point is 188, whereas for argon it is 87. In the case of argon, it's only the London dispersion forces that come into play. In the case of HCl, we have the London dispersion forces and the dipole-dipole interactions. And again, you can check it out and explain which one has a higher boiling point, or which one would you think would have the higher boiling point. Both the compounds, ammonia and dinitrogen oxide, both are having different molar masses. Both are polar. In the case of ammonia, there is a hydrogen bond. In the case of dinitrogen oxide or nitrous oxide, we have no hydrogen bonds. And as we continue along, the remaining few questions are for self-study. Please do check it out and make sure that you understand the concept as well as a concept and the reason for the selection of your answers. With that, I'm going to stop it here, and then we'll complete it for the next session, the last unit that is present.